Welcome. So this video I'll start discussing numerical methods for nonlinear MHD or other fluid kind of problems. And these are a little bit different from linear problems in that there are a lot more issues to consider because the nonlinear effects can cause transfers between scales, can lead to large changes in things like density and pressure, and so these can lead to various problems that we need to consider. And so things like conservation of energy, for example, tend to be much more important for nonlinear problems than for linear ones. So small errors like this in linear problems just give a slight deviation in the growth rate, for example, whereas for nonlinear problems, things like conservation of mass or momentum or energy can lead to numerical instabilities, which end up completely destroying the solution. So in this video I'll summarize some of the issues to consider when thinking about and designing numerical methods, and then I'll focus on conservation and different ways that we can conserve quantities and need to think about conservation properties. So some of the issues you need to consider when you're designing numerical methods are first conservation. And so this is things like conservation of mass, momentum and energy. Strangely, mass and energy are probably easiest to conserve. So mass is definitely the easiest one to conserve. Energy probably the next one. Momentum can be quite hard to conserve in general coordinates. So if you have some curvilinear coordinate system and some quite complicated fluid equations, momentum can be quite hard to conserve. You might also want to conserve, in addition to these sort of basic quantities, you might want to conserve things like entropy, or at least ensure that entropy is not decreasing. So you might at least guarantee that entropy can't decrease. You might also in some cases have things like entropy, so in two-dimensional incompressible flow, entropy, which is the square of the vorticity, can also be conserved. And there are various other high-order terms, so helicity we've come across as well as a quantity that might be conserved. And so all these quantities you might or might not want to be conserved in particular cases. And we'll see that if there are particular quantities you really must conserve to machine precision, then ideally they're one of the quantities you evolve explicitly. So if you want to conserve mass, for example, one of the evolving quantities might be the density within each cell, because this makes conservation properties much easier, as we'll discuss very shortly. The other issues are things like stability, and this of course comes up in linear problems as well, but here it tends to be more difficult because you have things like velocities changing in time, and so the CFL condition, which places a limit on the time step, is also changing in time. So the time step dt is changing, and so you might need to have more sophisticated methods to track the time step, or to enable it to vary in time. So there are lots of adaptive schemes to change the time step or change the order of accuracy. And the other thing about nonlinear schemes is energy transfer. So for example, if you think about turbulence, you start with some large fluctuations. Those fluctuations break into smaller fluctuations, and the smaller fluctuations break into even smaller, and so there's a transfer of energy from big scales down to small scales, and eventually those scales reach the scale of the grid. And so you need enough dissipation at small scales, either physical dissipation, or so physically realistic dissipation, or some numerical dissipation, which will prevent the scales from becoming smaller than the grid scale, and then you end up with numerical oscillations and various aliasing effects, and that typically some kind of numerical instability. And so you need dissipation of some kind. And in some cases, the physically realistic dissipation is enough if you have a high enough resolution in your grid. But in other cases, you might have to have additional numerical dissipation just in order to stabilize the method. There are other things which are can also be important. So so physical constraints, call them. So these are additional constraints or limits on your solution, which are not necessarily enforced by the numerical method. So in addition to conserving mass, for example, you also need a constraint that the density is always bigger than 0. Here's an example. And so there are various numerical methods which can work to high accuracy. They're stable, but they don't necessarily guarantee that density is positive. And this is typically a problem when you have very big gradients or very low densities. So the edge of tokamaks, for example, this can be a problem. For example, if you look at if you have a sort of simple one-dimensional, it's like x. If you start with a density which has a kind of very low density and then some kind of very steep gradients like this. So this is the density, for example, and then you evolve it in time, so some kind of advection problem. What will typically happen is that you'll end up with, for many schemes anyway, you'll end up with so I'll draw the red is after some evolution, some time. So you'll end up with some kind of oscillation like this. So this part might be quite accurate, but you'll end up with essentially oscillations either after the pulse or before the pulse, depending on which scheme you're using. So Lax-Wendroff or beam warming, for example, or second order central difference will give you oscillations basically everywhere, unless you have some kind of dissipation. And then in these regions here, of course, you're going to have things like n density less than 0, and unless your numerical scheme can handle these can cause big problems, because in the momentum equation, for example, you have to divide by density to get the acceleration, and so this can then cause the whole system to blow up. So there are constraints on things like density. Same with pressure, also has a similar problem. Temperature, of course, in the same way, and there's things like entropy, which may also be a constraint. Another common one is if you're evolving magnetic field, you have to ensure that divergence of B is 0. It's an important constraint, and again there are many different schemes for doing this. And then finally, another aspect is the dispersion relation. For various waves. So if you, depending on what kind of problems you're looking at, if you're looking for a very robust scheme, say you have shocks or you have just flows through pipes or all this kind of stuff, then you might just want a very robust scheme which works well for large jumps, for example. But typically those schemes will have dissipation which turns on and off, and in order to avoid things like this density going less than 0. And these can actually have bad effects when you try and solve for waves. So if you're not interested in large jumps or very large fluctuations, but instead you want to get the dispersion relation of the small waves correct, then you may need different numerical schemes. And typically there you want linear schemes, things like second order central difference, perhaps with some dissipation to control the numerical instabilities. But typically if you don't want some kind of a nonlinear limiter schemes. So here if you want accuracy for small waves, there's a trade-off between accuracy with for small waves and robustness with large fluctuations. And so with any numerical scheme, there are trade-offs to make between what you care about, what your numerical method is designed to do, and this depends on the kind of problems that you want to solve. So whether it's looking at the interaction of small waves, or whether it's looking at very large fluctuations, what are the quantities that you want to ensure are preserved. So for example, if you're looking at fluctuations in the core of the plasma, typically this density constraint is not a big problem, because if your density has small oscillations, the background density is so high that you're very unlikely to get negative densities. Whereas in the edge of the plasma, this can be a big problem, and that changes the choice of numerical schemes.